Welcome to Higher Structure Seminar Series. Uh, Today our speaker is Asgar Jamneshan from TU Dresden, and we are very to have him here as our speaker. And he will tell us about some applications of topos of measure-theoretic sheaves. So please, Asgar.
So thank you very much for having me. So I will start with some motivation, and actually, I will somewhere in the middle of my talk introduce the topos of measure-theoretic sheaves. So I start with a simple example. So that's a theorem we all know from real analysis. So if you have a continuous function on a compact Hausdorff space with taking values into the in the real numbers, then this function is bounded and attains both a maximum and a minimum value. So how is this theorem usually proved? So historically, the first case where this theorem was established was for the compact interval in the real numbers. And two main ingredients go into the proof. This is on the one hand the Bolzano-Weierstrass theorem, which says that any bounded sequence has a converging subsequence, and then the Dedekind completeness of the real numbers, which says that any bounded subset of the real numbers, regardless of cardinality, has a supremum and a minimum. Okay. So I want to randomize this statement of the extreme value theorem. And the first suggestions I want to do is quite common in certain areas. I will mention them in a few slides. So we take a probability space and then we look at what is called a compact value correspondence. So a correspondence is a set valued map. So for each point in the probability space, we associate a compact subset of the real numbers. And then we have also a bivariate function, f. You can see this as kind of a random real function where we assume that for any given x, so for any point in our probability space, the function is continuous in y. Okay. Now, what we would like to do is that, of course, we can, if we fix x, then we can just apply the extreme value theorem in y, right? Because for any kx, so kx is a compact set, and we want to compute the infimum of this function for a given x. But the question is because under which conditions, assumptions, is this function measurable in x? Okay. So this optimal value function. And then there is a classical theory, which goes by measurable selection theory, which says that, so we can here apply the Kuratowski-Rilnach-Tversky measurable selection theorem, which says that a sufficient condition for this optimal value function to be measurable in X is that this compact valued correspondence satisfies what is called the Effross measurability. So what does Effross measurability say? It says that if I take any kx, so any compact subset which is a value of this function, and then the set of points x such that ks intersects non-emptily any open set should be a measurable set in the probability space. Okay, under this condition, and if we assume that the function f is what is called the Kara-Theodori integrand, which is a very natural assumption, namely the function f itself should be already measurable in x for fixed y. Okay, otherwise, if the function f is itself not measurable in x for fixed y, then there is no hope to guarantee that this optimal value function is measurable. So under these two conditions, so the second one is quite natural, though the first one is a rather technical assumption, and this technical assumption is mainly motivated by the existing, by this measurable selection theory. So that guarantees that this optimal value function will be measurable. And so this area of measurable selection theory, so that was just one example of many. It usually, like if you want to look at it from a methodological point of view, it usually works as this. So we have like some deterministic results, say we want to randomize it. Then the way what we do is that we pointwise formalize it, as I did in the previous slide. And then in each fiber, we apply the classical theorem, like as we did in the last slide. So the classical theorem was there, the extreme value theorem, and in each fiber of the probability space, we applied this. But then we would somewhat guarantee that the outcome is measurable, and then one usually has to establish sufficient conditions for the existence of such measurable selectors, they are called, from this fiber formulation. And there are some restrictions in the theory, such as separability, and these set-valued maps, they should be closed-valued. Okay, so for example, if you're interested in open-valued correspondence, and this measurable selection theory not always works. Or if you are interested in working in spaces which lack separability, for example, if you would like to like, for example, instead of the real line, you would consider, for instance, an inseparable vector space or something like this. So these assumptions cannot really be relaxed. For example, one thing what one consider is that instead of requiring these properties to hold in every point, since we have a measure, we could ask that these properties hold almost everywhere, so outside of a null set with respect to this measure. But that also doesn't help much to relax these sufficient conditions which are needed for measurable selection theory. And measurable selection theory has a number of applications. For example, in stochastic programming, if one wants to do portfolio optimization dynamically over time, or a differential occlusion, then calculus of variations, you have usually like an energy minimization problem where you have an integral where you have a parametric function inside it, and also in mathematical economics, for example, and other areas. So it's kind of a useful tool. Now, I would like to suggest a different formalization. Instead of formalizing such problems pointwisely, I would like to take a point-free approach. So in this case, what I do, I first consider the space of all measurable functions from X, from the underlying probability space to R, and identify two such functions if they disagree on a null set. Okay, so that's the usual way how one constructs LP spaces. L0 is the largest of such spaces. It is just a space of all measurable functions. So now in this space, there are no points, right? Because every function is like an equivalence class of functions. So we cannot really talk about point evaluations of such functions or of such equivalence classes. Now we can equip this set with almost sure addition. So we can add two function almost surely or multiply two function almost surely. And we can also compare two functions because they are real valued with respect to almost sure ordering of two functions. In that case, this space L0 becomes an ordered commutative unital ring. It actually even becomes a Ries space if you consider the ordering, okay? So now there are two essential choices, so at least in the literature, how to consider convergence on so a topological structure on L0. So one is a topology of convergence in probability. This topology is metrizable, and it's also a ring topology. That's a fact which is lesser known, actually. So it makes this ring operations continuous. And there is almost sure convergence of measurable functions, but this almost sure, the notion of almost sure convergence is not even topologizable in general. So there is no natural topology on L0 corresponding to this concept. So now let's introduce another topology. And the way I want to build this topology is a little bit the way we built the topology on the real line. And we will see how this is related to topoi later. So we take two functions, f and g, such that f is smaller or equal to g almost surely. And then we can consider this random interval. Like you can imagine this. So this we consider all h. So this is a point-free object, right? Because all these functions involved here are equivalence classes of functions. But we can consider the set of all functions which lie between these functions f and g. So in general, like in general, I mean in general for all probability spaces, underlying K is not compact in the topology of convergence and probability. Okay. Although this random interval or random closed interval you want to consider is closed under almost sure convergence, and obviously it is bounded with respect to the almost sure ordering. Okay. So the question is, can we make sense of this notion of compactness, which is kind of hidden here in a certain way? So let's consider a certain topology. That's a classical topology on this space. So we can consider what is called also in the literature the order topology. So we take open intervals on L0 for any two functions where f is strictly smaller than g almost everywhere. And then we can take this as a basis of a topology, and we can consider the topology generated by such random open intervals. Then this will be a ring topology, and it is much finer than the topology of convergence and probability. And what is also important, and that's very important for what will come later, is that these open intervals have the following concatenation property. So if I take a partition of my underlying probability space, a countable partition into measurable sets, and I take a sequence of functions in this open interval, then I can concatenate these functions along this partition. Okay, this countable function h in this open interval, which coincides with hn on each of these measurable sets an. Okay, so this open interval is closed under countable concatenations. Okay, so you can see this a little bit if you're familiar with sheaf theory as a gluing property, and you will see that this connections is actually quite tight. So that's not a coincidence that this property holds here. So, and then we now introduce another notion of compactness. So a collection C of subsets of L0 is said to cover a set X. If, so set here X is, sorry, that's bad notation because I was also denoting the probability space with X. So X is here, by X, I mean here a subset of L0, not the underlying probability space. I'm sorry, that's a bad notation here. So the collection C of subset of L0 is said to cover some subset of L0 if for any element in this subset, so for any measurable function in this subset, there exists a partition such that, and a sequence of elements in this covering collection, such that I can locally cover these functions in each of those covering elements. Okay, so that's not a classical notion of union, so that you can basically cover some subset with other subsets, but that's a kind of a union up to this countable concatenations. Okay. And now I can say what is a compact subset in L0 or this other notion of compactness. So I say that a subset in L0 is compact if every covering, which consists of these open intervals introduced above, there exists a partition of the underlying probability space. And for each element in this partition, there exists a finite subcollection of this covering set, such that every f is locally along this partition in some of these finite sets along, okay? So basically, the classical notion of compactness says for every open covering, there exists a finite subcovering. And this notion of compactness says for every open covering, there exists a partition such that on each element of this partition, I find a finite covering, and I have to glue functions together in order to fall inside that covering. Okay. And if you assume this notion of compactness, then this interval, this kind of closed interval which we introduced satisfies this notion of compactness. And now I can formulate another version of this randomized extreme value theorem. I call it the measurable extreme value theorem. So let f be a function from this random interval into the space of all continuous on all of all measurable functions. And suppose it is continuous in this interval topology, which I introduced before. And this function respects concatenation. This means that if I concatenate a sequence of function in this random interval, and then I apply the function, then it is the same as I would first apply the function to each of the elements in this concatenation and then concatenate. So concatenations and evaluating the function commute with each other. Okay, so that's an extra property I need here. In this case, one can prove that f is indeed bounded. So bounded in the sense of this interval topology. Okay, so it can be bounded by measurable functions. Those measurable functions, of course, could go to infinity. So but it is bounded in this sense, and it attains a maximum and a minimum with respect to this almost sure order. Okay, so that you can consider as a measurable version of the extreme value theorem. So how can you prove this? Actually, with a similar effect as before. So one can show that the space of all real valued measurable functions on a probability space with respect to this almost sure pointwise ordering is Dedekind complete, meaning that any bounded subset, regardless of it is a countable or uncountable set of measurable functions, which are bounded in this almost sure ordering, has a supremum and has a infimum in this ordering. Okay, that's actually for people coming from measure theory at the beginning not obvious, because usually we learn that only countable supremums and infima of measurable functions are measurable. But but this is for pointwise order, not almost sure order, because we are allowed here to kind of throw away null sets. One obtains this Dedekind completeness for L0. And there is also a type of Bolzano-Weierstrass theorem. So if Fn is a bounded sequence in this sense, in the L0, then there exists an increasing sequence of random indices. So these indices are now functions which map into, so are random functions in the natural numbers, which increase, such that if I parameterize this sequence of functions with this random index, then they will converge to some function f almost surely. Okay, so that you can kind of view as an measurable version of the Bolzano-Weierstrass theorem. So now, in fact, this one can actually show that this whole approach, which I just exemplified, actually in some sense generalizes measurable selection theory. So for example, one can show that there is a one-to-one relation between compact valued Efros measurable correspondences and these kind of compact subsets of L0, which I just defined. One can also show that there is a one-to-one relationship between these Carathéodory integrands. Recall these Carathéodory integrands were these bivariate functions which were measurable in X and continuous in Y. And one can show that there is a one-to-one relation between these and continuous functions from L0 to L0 with respect to this interval topology, which respect countable concatenations. And but one advantage of this approach, which I just showed, is that it generalizes. So you can take also values in inseparable spaces, and this notion of compactness is flexible. And one also does not necessarily need closed values Efros measurable correspondence, which guarantee measurable selectors, but one can choose any subset of L0, but under the assumption that it is closed under countable, so it allows this gluing property. Okay. And how is measurability guaranteed? So in the measurable selection theory, the measurability would be guaranteed by applying um, uh, pointwise a classical theorem and then somehow extract a measurable selector under certain necessary assumption. But what we do here, we do not apply pointwise classical theorem, but we prove measurable versions of classical theorem, such as a measurable version of the extreme value theorem, which I have just shown you. And the outcome of these measurable, so applying such measurable versions will automatically guarantee measurable outcomes. Okay, because the way these theorems work is that the outcome of applying such theorem is automatically measurable, and this does not depend on any countability or separability assumptions on the underlying spaces. So that's what I just explained, but there are some assumptions needed. So one needs that the underlying measure space is sigma finite. So I just talked about probability spaces. Then the second thing is that all objects must be identified almost surely. So all the objects which are involved in the reasoning one wants, and they have to respect countable concatenations. So let's see that what I have just outlined is actually why is it true? It has actually some deep reason because it's actually what I just show is the internal. So for those who are familiar a little bit with topos theory and logic, it's actually the internal logic of a certain topos. So let's see how this topos is constructed. So what we will do, we will take the probability space, and then what we can do with this probability space, we can associate to it a measure algebra. So what is a measure algebra associated to a probability space? You take the sigma algebra F and quotient out the ideal of null sets. This gives you another quotient Boolean algebra. It's not necessarily an algebra of sets. And this quotient algebra satisfies two important properties. So first of all partitions in this quotient algebra, because mu is a finite measure, are at most countable. And completeness, and this is the striking property, this quotient algebra is actually closed under arbitrary unions and intersections. So a sigma algebra of sets is usually only closed under countable intersections and union. But once you quotient out the sigma ideal of null sets, and given that mu is a probability measure, then A has a stronger property, this quotient algebra, namely it is closed under also uncountable unions and intersections. Okay, so here we have now a complete Boolean algebra A, and we can define a site on this complete Boolean algebra. Okay, so J, the way this site works is as this. One takes an element of this complete Boolean algebra and associates to it the collection of all partitions of this element A. And then one can show that this is a Grothendieck basis for what is called the subtopology on A. So there is a notion of subtopology on partially ordered sets, and this gives a site. And now we can construct a Grothendieck topos of sheaves on this site. Okay. So now this topos has a particularly rich internal logic. So it has a natural numbers object. The logic is Boolean, and the reason for that is because we started with a complete Boolean algebra, and it satisfies the axiom of choice. In fact, one can show that such a topos is what is called in logic a Boolean valued model of set theory. So that's a quite strong transfer principle. That means that in such a topos, every theorem of set theory, so every theorem of Zermelo-Fraenkel set theory, has truth value 1. Okay, so but you need to reformulate this theorem. So there is a transfer principle which reformulates. And actually, that measurable version of the extreme value theorem we just showed is an example. That's actually the extreme value theorem in this topos. Okay, so this topos has an internal logic, an internal discourse. For example, let's see a few other objects. So we can make now the space L0 to be a sheaf in this topos. And the way we do this is just by restricting by the restriction operation. So we have, if you have two measurable subsets, A smaller than B, or A included in B, then we can consider the measurable functions on B and can restrict them to measurable functions on A. Okay. And with this restriction operation, one can show that these sets become a sheaf. Okay. And the gluing property is exactly that. Gluing property is a countable concatenation property of measurable functions, which was mentioned before. And one can show that this L0 space is actually the real numbers in the internal logic of this topos. And this measurable version of the Bolzano-Weierstrahl theorem, which I just showed, is an external interpretation of the internal Bolzano-Weierstrahl theorem inside this topos. Okay. One can also describe the power set. I want to just illustrate to you some basic operations in this topos. So let's look at the power set of the real numbers inside this topos. So you can describe it in the following way. So these are pairs where X is a subset of L0, which is closed under countable concatenation. So you can glue the functions inside X along partitions. And A is some element in A. Okay, so now let's see how the union works. So that's the union. So suppose this is a local subset in L0. So it lives just on this measurable set A. And this is another local subset in L0, which lives on the measurable set B. So if you would take, so you what this block here means is that you take all measurable functions like which lie somewhat inside this range in R. Okay. And now suppose you would like take the union of these two. Then this would not be the union in this sheaf, in the sheaf topos, but the union would also be considering the gluing of elements where locally the element lies here a little bit, and then the rest of the element lies here. Okay, so that's the notion of gluing in this topos. So let's look at the notion of intersection. Here again, we have two sets. So X consists of this block and this block. So these are measurable functions which lie somewhat here, and they live locally here. And then Y is this orange part and the pink part, which is another set. But now if you form the intersection, in fact, if you would form the classical intersection would be empty because there is no measurable function which lies fully here and fully here. But this locally intersects in this topos. So the intersection actually in this topos is somewhat not empty. And this is a complement. So suppose you want to form the complement of this set, then this set locally can be everything. And somewhere it can be something, and it can also somewhere else locally be just nothing. But then the complement you would construct is like where it is nothing, you would take everything. Where it is something, you would take something which is everywhere outside. And where it is everything, you just take nothing. For example, this measurable function is not in the complement. Why? Because with positive probability, it would fall into this green set, although this measurable function in black would be in the classical complement of this set. Okay. So now we can construct actually measure-theoretic sheaves out of any measurable space. So we just looked at the L0 space of functions mapping into the real numbers, but instead of the real numbers, you can take any measurable space, E with some sigma algebra, calligraphic E, and then you can look at all measurable functions from X to E, where you identify two functions almost everywhere. Then this is also a sheaf in this topos. Okay. Or you can do something a little bit more fancy. So for example, you can take E to be a Banach space, and then instead of considering all Borel measurable functions, you only consider what is called strongly measurable functions. in vector analysis, that's an important notion. So these are only measurable. So if E is inseparable Banach space, then Borel measurable functions are not necessarily strongly measurable. Strongly measurable functions are Borel measurable functions with a separable range inside E. Okay, and then in this case, one can equip this sheaf with a norm. This norm is like a random norm, as you see. So it maps x to the norm of f of x. Okay. So it's a measurable function. Actually, we need strong measurability in order to make this norm measurable. And then one can show that with this measurable norm, this space here becomes an internal Banach space in this topos. And then there are some other construction one can do. One other construction I want to point out is the following L2 space. So suppose G is a subsigma algebra. In this case, we have this notion of a conditional expectation. So that's basically the orthogonal projection onto the space of G measurable functions in L2. And one can take all functions in L0, which have whose square has a finite conditional expectation. Then one can show that this space here, which I call the conditional L2 space, is actually has an inner product defined with this conditional expectation, and this space becomes an internal Hilbert space. And I mentioned this space for two reasons. So one reason is it is not of the form above, okay? And it is also important in ergodic structure theory, this space. Okay. So now I want to give you actually two applications to ergodic structure theory. Maybe I should stop here and see if there are any questions. No? Okay, then I maybe continue. So suppose we have an arbitrary discrete group gamma and let A mu be a probability algebra. So that's just a measure algebra with total mass one. And we denote by out this the measure preserving Boolean automorphisms of this space. And then we can define a measure preserving dynamical system to be a tuple where this is a probability algebra and T is just a group homomorphism from the external group gamma into this automorphism group. Then one can also define the notion of a factor in this for measure preserving system. So that's actually a subsystem. Okay. So that's another system such that there is a Boolean homomorphism from B to A, and such that this Boolean homomorphism intertwines the action. Okay, so this shows that this B can be realized as a subsystem of A. So one has also a Koopman representation. So you can take gamma. So that's actually a unitary representation of this group. You can lift this measure preserving action on the space to an action to a unitary representation on the corresponding L2 space. And there is a classical result which goes by the name of the Jakob de Löw-Glücksberg decomposition, which shows that this L2 space can be decomposed into an orthogonal sum, where AP somehow represents the compact part. So that's actually all the finite dimensional representations of gamma. And WM, which is a weakly mixing part, is somewhat the random part of the system, or the part which does not admit any finite dimensional representation. So this primary decomposition is useful, but it does not capture all the structure which could be in a system. I want to give an example. So
Uh,
let's consider
can I
just
ask one question?
sure.
I'm sorry. Gamma here in the Koopman the representation is a topological group or just a discrete? group,
It's just a discrete group.
discrete, infinite discrete group, probably.
Yes.
Yeah, thank you.
So you can, so let's see the following example. So consider as an infinite group, we take just the integers and, oh, sorry. And then as a base space, we take the two torus. Okay. And now we have the following dynamics. So on the first component, we move by some alpha. Okay. That's, you can consider an irrational rotation. But then in the second component, we move with x, where x is the first component. Okay, so the movement in the second component depends on the base point x. One can show, if one considers this decomposition, that the almost periodic part of this system is just this rotation in the first component. Okay, and relative and however, this system is pretty structured. So because if you look relative to this rotational factor, then the whole space also behaves kind of almost periodically, right? Because actually we have another rotation in the second component, which depends on the base point. But this decomposition does not see this extra structure because that's a kind of structure relative to something else. Okay. And in order to understand this, so this is an example of a system which is goes by the name of a compact extension or structured extension of a compact factor. And in order to understand the representation theory and classification of such compact extensions, one needs a formalism where one is able to perform analysis relative to a factor. Okay. So, for example, such a decomposition, but relative to some other factor. Okay. And in order to do this, so classically, this can be done for countable group actions or for separable probability spaces using measurable Hilbert space bundles and direct integrals and disintegrations of measures of this factor map. Okay, this is very similar, the approach, as the approach I outlined in the optimal value problem, where you would do a fiber-wise, point-wise analysis. And it also suffers from the same restrictions because measure disintegrations, for example, only exist if those underlying probability spaces are countably generated or separable. Okay, it does not apply to all probability spaces. So alternatively, what one could do is that one can translate this decomposition problem or this understanding this compact extensions into this topos of measure-theoretic sheaves, where one now takes the builds the sheaves on the subspace algebra. Okay, so you have a subsystem, and on this subsystem algebra, you can form the sheaves. So that's now the because you want to relativize towards that. So that's where you build it, and then you can do the representation theory of these compact extensions. Is actually nothing else. You consider this sheaf which I introduced before, which is like this conditional Hilbert space. And then you can do actually the same decomposition relative to this subsystem. And I have shown in a paper, I mean, you can do it by hand, but you can also by basically imitating the internal logic in this topos. But in fact, this would already follow from a transfer principle because we know that these topoi have a strong internal logic. So actually the relative version of this decomposition would be just a transfer principle applied to this decomposition in a suitable topos. And then, and this has, by the way, there are some, so this kind of structure theory plays a role, for example, in Fürstenberg's proofs of Samaredi theorem. It has also named Fürstenberg-Zimmer structure theory, and it has some relevance in certain areas in ergodic theory and also in applications to combinatorial number theory. So maybe I skipped the second ergodic theoretical example. It is an example from measurable cohomology. And Or maybe I give this example and skip the last example, which is in vector duality. So this example, now we assume that the group is abelian and we have a abelian system. So this could be, for instance, an infinite abelian group, and then discrete, and then we have a measure preserving system with respect to this abelian group. And now let K be another compact abelian group, and then we define a cocycle. So that's kind of a dynamical, sometimes these are called also measurable cocycles, is a map from gamma times x to k, which satisfies the following cocycle identity. So if I add two elements in the group and I apply the cocycle, then this is the same as first applying the first element plus applying the second element, but moved by the first element. So a cocycle is a coboundary if there exists a measurable function from x to k such that basically the cocycle is a derivative. Okay, so it's f composed with t gamma minus f. And now we have a classical theorem of Moore and Schmidt, which gives a criterion how to check when a cocycle is a coboundary. And that's kind of important in certain applications to be able to check for a cocycle. And here K is just an abstract compact abelian group. But this condition of Moore and Schmidt tells you that it is enough to check this on the torus for cocycles with values in the torus. Because a cocycle is a coboundary, if I compose this cocycle with characters of this group, which map into the topos, if any composition with a character is a coboundary. Okay? So the way to prove this result, you can pointwisely formalize this theorem, and then one needs some restriction, gamma being a countable group, K being a metrizable compact abelian group, and the underlying probability space being countably generated. So what we did with tau was that we gave a point-free formalization of this theorem, and we could generalize this theorem to actually X mu could be any measure space, and not only a probability space. Gamma could be any discrete abelian group, and K could be any compact abelian group. And the way we did this is that we used somewhat, I mean, we didn't write it in this way in the paper, but we basically used an internal Pontryagin duality between compact and discrete abelian groups in this topos of over the measure algebra of this probability space, underlying probability space. Okay. So I have one more application in vector duality, but I think maybe I skip this and stop here. Thanks.
Thank you very much, Asgar. Any questions or comments? So maybe I will ask one question. Uh,
Sure.
you said that the decomposition of the representation has topos of measure-theoretic sheaves interpretation, or one can rephrase it in terms of topos of measure-theoretic sheaves. So, for example, if we have, let's say, uh, a Lie group, and if we consider representation, unitary representations of, let's say, semi-simple Lie groups, we have a decomposition into discrete part and continuous part and so on, which resembles Gutmann decomposition. Can
Mhm.
one rephrase Harishchandra's theory in the language of topos of measure theoretic sheaves? That's my question.
So I am not very familiar with this part of representation theory. So one question is that um, what are the Hilbert spaces on which you represent?
L2, L2. They are all L2 spaces. If G is our group, G quotient out with some,
I see.
let's say, co-compact quotient, maybe. Yeah.
And then what is the theory of this uh,
So,
Harishinda?
yeah, I mean, the brief summary is that we can decompose the representation into a discrete part and another part which is an in how should I say, which is a integral part, a continuous part and discrete part. We have discrete subspaces and
Okay,
uh, a continuous direct sum. So they write the integral with a
I
direct
see.
sum on top.
Um, so I'm not sure because so this classical decomposition for this one doesn't need any measure theoretic sheaves.
I see.
Yeah,
Uh-huh.
that is only needed in the relative situation where you want to establish. So, for example, in the example you mentioned, if you would want to, for example, have a representation relative to some other behavior on the leap group
I
or
see.
conditioned on some other assumptions which you have or on some then this theory could be made fruitful.
I see.
Yeah,
Okay. Oh, great. Thank you.
sure.
So, any more questions or comments? So, what are the references, by the way, of all these works? I mean,
I'm happy to send them to you.
okay, excellent.
Yes.
So, let's thank Oscar once more.
Mhm.
So, we will meet 2 weeks from now. So, see you all later, 2 weeks late from now.